Welcome everyone, and thanks for listening to our presentation about dynamic simulation of bath copper converting using SysCAD with ChemApp. We are pleased to share with you today at the GTT 2022 Annual Users Meeting. My co-author is Kevin Hepner. He's a Senior Process Simulation and Software Engineer at SysCAD, and my name is Tanai Marin. I'm a Senior Simulation Engineer at SysCAD. I'll start by giving a brief overall description of copper bath converting, followed by the details of thermodynamic systems and data used for this model, the implementation of the model using SysCAD Dynamic Solver and the ChemApp interface. Then we will show and discuss the results of a full converting cycle and the various parameters calculated. And we will finalize with conclusions and next steps for the model. SysCAD is a powerful and versatile plant simulator. It can be used to simulate anything from the simplest process circuit to a complex full plant operation. When used to its full potential, it can serve in every aspect of the plant life cycle, from feasibility study, design, commissioning, operation, and maintenance to expansion. It is an invaluable process design tool that will help users gain tremendous insight into their process operations. This knowledge can translate into better decision-making, improved plant operation performance, cost saving, and more efficient and knowledgeable operators. SysCAD simulation can be performed using under both static or pro-bal mode or dynamic modes. SysCAD can seamlessly link with a number of high-accuracy thermodynamic packages, one of them being ChemApp, which is the focus of this presentation. SysCAD integrates with several thermodynamic calculation engines, TCEs, the capabilities of which span from low-temperature AQ systems to high-temperature mixtures of molten metals, slags, and gases. SysCAD integrates with AQSol, OLI, FreakC, and ChemApp, which allows the use of FACSH-generated input files using the FACSH family of products. The solution provided by SysCAD is very flexible and allows to add specific unit operations using complex thermodynamic engines only when needed. In addition, the same SysCAD model can use multiple instances of one TCE, for example, several ChemApp systems, or even add multiple TCE units to a single model, for example, to simulate a process requiring AQs and high temperature thermodynamics simultaneously. Today, we will demonstrate the use of ChemApp interface in the context of setting up a dynamic model of batch converting process for copper matte. The model we present today is a traditional Peirce-Smith copper converting. As it is well known, this is a batch process in nature, therefore it's perfectly suited to demonstrate SysCAD's dynamic mode solver. Moreover, this process is typically composed of two different steps, namely the slag blow and copper blow. From a chemical point of view, it's important to separate these two distinctive steps to maximize copper recovery, since it is necessary to remove the slag produced during the iron removal steps and avoid overoxidation of copper. There is also an important consideration from the thermodynamic point of view, which is the pronounced non-ideality of the system. In particular, the presence of a miscibility gap near the copper-sulfur binary, separating the sulfur-rich matte from the blister, which results in the coexistence of two liquid phases during most part of the copper blow. This added thermodynamic complexity and the time-dependent nature of the process makes the use of the combined SysCAD plus ChemApp tools the ideal approach to model this process. The contents of the converter are assumed to be at chemical equilibrium at all times. Before implementing the model in SysCAD, the first step is to specify the thermodynamic system to simulate the converted process. In this case, we focus on the primary copper smelting system, where a copper matte or sometimes a white metal is produced in a smelting furnace or reactor and fed to the Peirce-Smith converters. The main system components selected for this model are copper, iron, oxygen, sulfur, nitrogen, hydrogen, and silicon. These components generate all the mixture phases and pure compounds that are required, including the ideal gas phase, liquid matte or metal, slag, spinel, monoxide, etc. The ChemSage input file includes 9 solutions and 39 pure compounds, and it was created as a plain text file using published data in publicly available technical literature. Here, A couple of examples phase diagrams or liquidus temperature projections for the two main ternary systems involved are shown. On the top right-hand side image, the matte metal system is displayed. This system is modeled using a single solution model that is valid for the entire range of composition for the copper iron sulfur oxygen system. This figure shows a section of the liquid projection for the matte blister case, copper iron sulfur, where the steep miscibility gap at the copper sulfur binary side is clear, even at a high iron concentration. Similarly, the calculated slag liquidus projection and isotherms for the iron oxide, hematite, and silica system is shown in the bottom left image. The low temperature melting zone and spinel saturation surface that is typical of copper converter process is clearly seen in the 3D liquidus temperature plot. Once the thermodynamic system is defined and the ChemSH input file is created and validated, it is possible to start building the SysCAD model. A critical first step necessary when using TCEs in SysCAD is to create a proper mapping between the native SysCAD compound database and the list of compounds and end members defined in the ChemSH file. Generation of the required SysCAD configuration files can be done automatically using SysCAD ChemApp utility, which generates a phase mapping link between the two systems while generating a corresponding SysCAD database file. The mapping process is extremely important as it allows SysCAD to interact seamlessly between inputs and outputs of the TCE unit operations. That is, converting back and forth between SysCAD streams and TCE streams. For each TCE model configuration unit used in SysCAD, a different thermodynamic input file could be defined, allowing for increased flexibility when modeling large systems. In this case, one ChemApp model configuration unit was required. The image on the right side shows the mapping, which is done automatically between the contents of the ChemApp system and the SysCAD species database. The converting process is modeled mainly by a ChemApp tank, which is the model unit containing and recycling the products of ChemApp calculations after each iteration. Fresh material can be added as a function of the stage of the process, for example, simulating the addition of furnace mat at the beginning of the cycle or by activating the addition of blast air and flux during slag blowing. To make the model more versatile, reusable, and encapsulated, a converter class was defined using the SysCAD PGM programming language. This is a built-in programming environment which allows for user-defined custom routines and settings. In this case, the converter class specifies the various states that the converter can be. For example, loading, slag blowing, skimming, copper blowing, casting, idle, or waiting, or even down for repair. The result is an easy-to-read code file from which a user can review the PLC logic. The behavior of the dynamic converter depends on its state based on programming rules applicable in the class. Predefined events can trigger changes in the process. For example, when the iron endpoint target during a slag blow is reached, the slag skimming sequence is initiated. In addition, and to add flexibility to the model, a subclass for slag blows was defined. This is useful to allow modeling situations with 2 or 3 slag blows or to set different endpoints, targets, or operating parameters for each slag blow. The reusable converter class can be used to model multiple converters in a SysCAD plant model. Here is a view of the main converter class page generated by the PGM code. In this page, general process settings are set, for example, the size of the mat ladles, process temperature, flow rates, etc. Also, information variables can be displayed such as actual iron to silica ratio, percentage iron and sulfur in mat or blister, process state, etc. The slag blow subclass has its own page, where specific parameters for each slag blow can be defined. In this example, settings for a converter cycle with 3 slag blows are shown. These figures summarize at a high level the overall logic of the model. Once an instance of the converter class is defined and the dynamic model starts, the converter follows some initialization routines and sets its state to idle. At this point, it's waiting for fresh mat addition, and depending on which slag blow it is, it loads mat until the prescribed number of ladles is met. The initial mat composition used in this example is such that both slag and copper blows are required. In this case, containing approximately 12.3% iron and 65.1% copper by mass. For example, the first slag blow was said to receive 3 matte ladles, followed by 2 and 1 ladles for the second and third slag blows respectively. During each slag blow, blast air and flux are added mainly to remove iron from the mat to the slag face until a set iron endpoint is reached. This is followed by a slag skimming sequence until the amount of slag remaining in the vessel is less than the minimum target. If the number of slag blows is still less than the specified number of slag blows for these cycles, then the process of loading, slag blow, and skimming is repeated. Once all of the slag blows are completed, the copper blow starts. Typically, the iron endpoint of the last slag blow is sufficiently low such that flux addition during copper blow might not be required. During the copper blow, the total sulfur content in the liquid matte or metal is monitored. Initially, only a high sulfur matte phase is present until the sulfur content reaches the miscibility gap at around 18% sulfur by mass. At this point, blistered copper appears and coexists with the matte phase. Although the overall sulfur content decreases, this is really the effect of increasing proportion of fixed sulfur concentration blistered copper and depleting of matte. Depending on the temperature and oxygen solubility, the sulfur solubility in blistered copper is around 1 weight% of sulfur. In this example, the copper blowing endpoint was set to 0.5% sulfur, which triggers the end of the copper blow and starts the casting sequence. This animation shows the model running during an entire cycle. The sequence of steps is pre-programmed as just described, where the various input and output streams interact with the main ChemApp tank unit representing the converter. In this example, the calculation mode is set to fixed temperature. However, the ChemApp tank also supports enthalpy target mode, where the reactor temperature is calculated based on a defined heat loss value. The sequence starts by loading 3 ladles of matte. The live trend on the right-hand side shows some of the calculated variables, with amounts of matte containing the converter in white, percentage iron in matte in red, percentage sulfur in matte in yellow. The iron endpoint for the first blow was set to 5%. Here, it is possible to see how the total amount of matte slightly decreases while the slag amount increases during slag blow. Also, based on the initial matte composition, a small amount of sulfur is also removed during the slag blow. After slag skimming, 2 additional matte ladles are added, resulting in the increase of total iron content to about 8%. This is followed by the second slag blow, also set to 5% iron endpoint, which in this case results in a relatively short blow. Notice how the oxygen dissolves in matte during the early stages of the slag blows. In practice, this type of model could help understand better the addition of flux to avoid precipitation of silica before the matte is saturated with oxygen. Before the last slag blow, the converter receives 1 additional furnace matte ladle, bringing the total amount of matte inside the converter to its highest level. The endpoint for the third slag blow was set to 1.5%, and due to the large amount of matte in the vessel, this results in a longer slag blow and amount of slag generated. At this point, the slag is removed in preparation for the copper blowing. The converter mainly contains matte at 1.5% iron, 20.4% sulfur, and 0.1% oxygen. The copper blow is the longest step as it needs to remove a significant amount of sulfur, approximately 80 tons in this example. At the start of the copper blow, the residual iron is oxidized and high copper oxide slag is produced. Simultaneously, sulfur is preferentially removed from the matte until the miscibility gap between the matte and blister is reached. In these trends, it is possible to observe how the amount of matte at the constant sulfur level decreases while the amount of blister copper saturated in 1.2% sulfur increases. It is interesting to see that at some point the amounts of matte and blister phases are reversed by ChemApp. Since the same phase model is used to represent both matte and blister phases, it seems that ChemApp arbitrarily assigns them to either matte number 1 or matte number 2, and at some point decides to reverse the labeling. Despite of this flip in metal matte phases, the model in SysCAD is sufficiently robust to continue the copper blow and properly detect the endpoint target for sulfur in matte. A possible enhancement that can easily be added to the model is the use of constrained free energy to oxygen in gas to limit the extent of equilibrium of oxygen, especially towards the last stages of the sulfur removal, where mass transfer limitations might start to become the rate limiting steps. At the end of the copper blow, about 14 tons of oxide are produced, which is consistent with industrial experience. Some of the residual oxide is washed or redissolved at the beginning of a new cycle, where 3 new fresh matte ladles are added. The process is then repeated. As an additional reference, this figure shows a snapshot of an entire cycle, indicating the various stages during the converting. The amount of matte is shown in red, blistered copper in blue, and the corresponding sulfur concentration are shown in yellow and orange for the matte and blistered phases respectively. To summarize, the bath copper converter model was implemented using SysCAD Dynamic Solver. The ChemApp TC interface was used to simulate the converter using a genetic tank unit model with a custom-made ChemStage file for this system. In this case, a pre-programmed logic was defined where the converter class interacts with various input and output streams. However, the same principle can be applied to a model interacting with real-time plant data, either offline, reproducing past cycles to validate and calibrate the model, or as an online digital twin of a converter, providing operators with real-time estimates of key process variables such as iron or sulfur endpoints, or giving recommendations on flux strategies or temperature management. The next steps for this model include finalizing enthalpy target runs and automate the addition of reverts and cold charge for temperature control, implement oxygen efficiency using the constrained free energy method to limit the extent of oxygen equilibrium, particularly as a function of sulfur concentration during the late stages of the copper blow. It will also be interesting to simulate multiple converters in parallel to simulate the sequence of an entire converter aisle, and add upstreams or downstreams equipment constraints such as furnace, oxygen plant, off-gas handling system, acid plant limitations, etc. Finally, expanding or enhancing the thermodynamic system by adding minor elements or impurities to increase the applicability of this model. Thank you very much for your attention. We hope you find this presentation interesting, and if you wish more information, please do not hesitate to contact us by email or through our website. Thanks.